So that's all I had about the GPT architecture, right? And as you see, right, I mean, once we know transformers, okay, once we understand the transformer architecture fully, which means the attention layer, the masking, the feed forward layer, the output, all of this, then as you study each of these large language models, there is not much to say about what the architecture is. It's just the transformer as you know it, and you just need to understand what the inputs are, what the outputs are, and the rest of it remains the same, right? So that's why it's important to spend a lot of time on the transformer architecture, the lecture on the transformer architecture, to make sure you understand it well. And as I go from one large language model to another, I'll not have much to say on anything related to the architecture. I'll just say this is the transformer block, this is the master attention block, this is the feed forward layer, and you would know all that based on the basic architecture. There has been not much, if at all, any innovation on these blocks. Whatever innovation is there in terms of using group query attention or multi-query attention, those things we'll cover as separate topics. But when I'm looking at a particular LLM like the GPT, I'll not have much to say about the architecture at all. I'll just tell you some numbers, that this is what the D model was, this is the number of layers and so on. But beyond that, what was the loss function, you already know. What was the architecture, you already know, right? So all of that is already understood. So that's all I had to say about GPT. Now what I'll do next is talk a bit about the difference between pre-training and fine-tuning. Okay. Yeah, so now that we have seen the GPT model, we will now talk about some generic concepts related to large language models, not specific to GPT in particular, right? The first concept of pre-training and fine-tuning. Most of you may already know this, but it's still good to formally look at it so that we can get it out of our system, right? So pre-training is what we have been talking about so far, where there is no supervision or explicit supervision. You get this automatic supervision from a large unlabeled corpus, where every next token is the label that you need to predict, right? So that's the implicit supervision that you are getting from there, right? And during pre-training, they used a batch size of 64. So your input size is batch size cross sequence length cross dimension size, which is 768. And you want to minimize for all the sequences. What this means, this complex notation, maybe I should simplify that. For all the sequences in your training data, for all the time steps in those sequences, for every time step, you need to maximize this probability. Clear? Okay. That's what we need to do. I don't know why this yi is here. Yeah, we just need to maximize the negative log likelihood of that probability, right? Negative of the log of y1 hat, right? Whatever has been predicted, which is the correct class label. Is that okay? Right? Okay. I'll modify this equation in the slides later on. Okay. They use Adam with the cosine learning rate scheduler. So we had seen this different learning rate schedulers, and we had seen this cosine learning rate scheduler, which sort of follows a cosine waveform. And we had also talked about teacher forcing when we had done transformers, that to make sure that the model during training, when it has the weights are almost close to random during the first few epochs, if you ask it to generate a token, right, and then feed that token as the input and then predict the next token, then there would be problems, right, because this itself is not very sharp yet. It is not really predicting the right token, and then sort of that error propagates throughout the network. Instead, you know what the actual sequence is because you have the training data. So you feed the right input at every time step. That's what teacher forcing is known at. So you do teacher forcing training so that you are feeding it the right input at every time step, the gold standard input, and not the input predicted or not the output predicted by the model itself, right? So that's what they do. And this, as we had discussed earlier, leads to quicker and stable conversions, right? Because initially it needs that help, and at some point you can remove those training wheels if you want. Now this was easy. Pre-training is what we have looked at. Now what is fine-tuning, right? So in pre-training, we really did not train the model for anything. We just trained it to predict the next token. But when you talk about a large language model, what do we want to do with it? We want to do several tasks with it, right? One task could be that, hey, here's a document and here's a review, tell me whether it's a positive review or a negative review, right? Or can you generate a summary from a given document, or can you tell me whether these two sentences are related to each other. So these are the standard NLU tasks which we would want to do it. Again, we are talking about very modern era of LLMs where we were still focusing on standard NLU, NLG tasks and not these extremely created user generated tasks that we do nowadays when interacting with ChatGPT, like asking a poem with a specific meter on a specific personality and so on. I'm not talking about those creative tasks, but standard NLU, NLG tasks like sentiment analysis, question answering and so on. Right? So we want those tasks to be done by an LLM, but we did not train it for any of those tasks. Right? We just asked it to predict the next token, and that's exactly the idea that we had. We wanted it to learn about language, and then we thought that once it learns about languages, I can teach it of specific tasks very quickly, and quickly here means with smaller amount of data. Right? So that's the idea. So that's what we do in fine tuning. We want to adapt the model for a specific downstream task. Right? So now we have small amounts of labeled data. So you have a list of reviews and the sentiment assigned to those reviews. This was positive, this was negative, this was neutral and so on. Right? So you have a sequence of tokens x1 to xm, which is the review, and the label y associated with that, and you have many such pairs. Okay. Yeah. So now now you could think of a network which takes, you could think of training a network which takes this review as input and it wants to predict some output which is 1 or 0, right? This is the network that you want to train. Now what network would you train? You just take your pre-trained network as it is, because it has already learned a lot of language. It is capable of taking input sequences of arbitrary lengths or up to the maximum length 5 and 2, right? It is capable of doing that. All you need to figure out is how do you ask it to generate the output, and then how you train it to generate this output given a new sequence, right? So that's what you need to do. So this backbone, you want to use the same as whatever you have done in pre-training, because now your belief is that the model has learned enough about languages. Our human analogy again, that you learn languages throughout your life. Now if I ask you to do a very specific task that, hey, read a passage and answer something, you are quickly able to learn that, right? So that quickly adapting to a downstream task is what we are doing now, and that's where fine tuning comes in. Okay. Yeah, and the input size, we will see how to modify the input and what you should do at the output. Okay, so that's what we are going to see. So the given input will pass through all the transformer blocks, and whatever the final token representation is there, right? This is the guy who has seen all the previous tokens. So it has the knowledge of everything that was there in the sequence, because for this token no masking applies, right? It sees everything. So whatever is the final output that we get here, we can use that to make the predictions that we want to make. So this final token representation has seen the entire document. Now we could choose to use that representation and then decide whether it's a positive review or a negative review and train the network accordingly, right? How to do that is what we'll see. So what it is saying is that you could add a linear classification layer on top of that. So this is your last tokens representation, which was 768 dimensional. You could add a W matrix here, which takes the 768 dimensional matrix and input and converts it into a zero, like a one dimensional output, which indicates 0 or 1, right? Is that okay? And suppose you have 10 classes, it will convert it into a 10 dimensional output, and then you will apply softmax on top of that to figure out which class has the maximum probability, right? Is that okay, everyone? Right? Okay. So we'll of course talk much more about this, and we'll make sure that this concept is clear. Okay. Yeah. So now our objective is to predict that label, right? So what is happening here? This equation sort of captures it. What is HLM? HL was the last layer that you have. M is the last token that you had. Okay. So this was all H1, H2, H3 up to H12, right? So L is equal to 12 here, and this was 512 tokens. So M is equal to 512. So you are taking that last token, you are multiplying it by W, so that it maps this 768 dimensional input into the number of classes that you care about, right? So maybe you care about 5 classes, very positive, positive, neutral, very negative, negative. Okay. And then on that you apply a softmax so that you get a probability distribution like this, and then whichever is the maximum probability, that will be your output. Or where during training you want to make sure that if this is the correct label, then this probability is maximized. Is that okay? So, we will maximize minus log y hat for the correct y. Standard training cross entropy loss. Is that okay, everyone? This is the objective that we will maximize. The probability of the correct class is what we want to be maximized, okay, and summed up over all the training sequences that you have, right. So, this is the true picture now. You had some reviews, right, and let us say you had capital N such reviews. For each review you also had the labels y1 up to yn. So, you are passing the first review to the network, which is already pre-trained. It passes this and computes this final representation here, right, that you pass it through a linear layer. So, which will give you then 5 classes is very positive, positive, neutral and all that, right, and then you do a softmax on top of that to get a probability distribution, and if this was the class that was the correct class, you just want to maximize this probability, and you want to do this for all the n examples that you have in your training data, right. And the advantage is that because you have pre-trained the network, you will have sample efficiency. That means you will be able to teach it this task with fewer samples as opposed to what you would need if you had not done any language pre-training. Is that okay, everyone? Right. So, that is how fine tuning and pre-training go together. Again, this wy, which is the new parameter that you have interested, is going to be trained, initialized randomly, and then it will get tuned using this data that you had, right. That is the only data available to train this wy. And if your sequences are shorter than 512 length, then you will have to add pads. If your sequences are greater than 512 length, you will just have to truncate at 512 because your network cannot deal with sequences of greater than 512 length. Okay. So, now let us see a few tasks. If it is sentiment analysis, right. So, this is what it looks like. You have a start token, you have an end token. This is your review. Here I am considering that the review had only 5 words. Okay. You pass it through the network, you get this representation, predict a distribution, and then you sort of back propagate through the network to make sure that the log probability for the right guy is maximized. Okay. And wy will get trained with that, and all these network parameters will also change to maximize this probability. Is that okay? Now, again there are 2 choices here. You can say that I do not want to change all this because I have put in a lot of hard work to train this using some billions of tokens. I do not want to change this. I will only adjust this and keep all of this same. This is known as freezing the network and just training the new parameters that you have. Alternatively, you can choose that the first k layers I will not train. So, you will freeze the first k layers, you will not back propagate through them, and you will only train the last L minus k layers and the new parameters that you have introduced. All of these are choices. Whatever works best, you can use that. But the idea is that now you are using label data because you have an x and you also have the true y for that x. Okay, so now let us see how to fine tune this model for the task of sentiment analysis, right. So, here is the text, so that will be fed as input. The sentiment is positive, so we want the class 1 to have higher probability than the class 0, right, if 1 stands for positive, okay. And so, this is how you will frame it, right. So, you will have this last dimension which is 768 dimensional, then your wy will map it to a 2-dimensional vector, and of that this class you want to maximize depending on which way you see +1 -1. One of those classes you need to maximize and you need to back propagate accordingly, and all the parameters of the network will change accordingly, right. Okay, cool. Now, let us see a few other tasks. So, the label data here is the following, right. So, you had n reviews given to you, this is one such review, right, and for each of these reviews, so this was your input x, for each of these reviews you know whether it is positive, negative, positive, negative, right. So, y is also given, hence the label is there. So, the x part goes here. During training you will pass it through the network will predict something, it will predict something for +1, it will predict something for -1, and your objective is to maximize the probability of +1, right, and this loss will be back propagated to the network, and the parameters theta of the entire network, that means the attention heads, attention weights, the attention parameters, the feed forward parameters, all of that will get modified, including this new parameter that you have introduced, right. Okay. Now, if you have textual entailment, right, so what do you have there? You have a text, okay, and there is a hypothesis, okay, and you want to say whether this is true or not. That means, does the text entail the hypothesis? So, he's saying that many males are playing a soccer game, and that means some men are playing a sport, which is of course true given the context. So, you want to predict true here, right. So, again here it could be true or false or maybe not related. So, there are 3 classes and there are 2 inputs here, right. Remember, there is the text and the hypothesis. So, what you do in such cases is that you feed the first text, you have a special separator, right, which says that now a second text is going to start, right. So, both of this you feed to the network. Again, the network does all the computations and computes a representation for this. And now suppose there are 3 classes that you are interested in, true, false, or can't say maybe, or unrelated or something of that, right. So, then this WY will take this 768 dimensional input and map it to 3 classes, and it will predict a probability distribution after applying the softmax. So, if this was the correct class, you take the minus log of that as the loss function and back propagate to the network and fine tune all the parameters. Is that okay? Right. So, fine tuning here, why is it called fine tuning and not training? Because you already have pre-trained the network, your weights are at a certain configuration, now you are just adjusting them for this task, as opposed to starting from a random initialization and then trying to adjust all the weights for this specific task. That would have been training. This is fine tuning. You are already at some configuration, you are just trying to adjust from there, okay. And you can just do this for other tasks. So, let us see. Now, here is a question answering, right, which of the following animals is an amphibian? So, frog or fish, right, this is a multi-choice question, okay. So, now what will I do? I will feed the question here, I will feed the first choice here, okay, and then I will calculate some linear representation for this, right. So, I will have some embedding computed here, okay. Then I will repeat the same with the second choice, okay. Now, I will pass the choice to, again I will have some representation computed. So, I will have the representation for the first guy, second guy, and so on, and using all of this, then I will compute a softmax depending on the number of choices that I have. So, if I have 4 choices, I will compute a softmax which gives me a probability distribution over these 4 choices. It tells me which choice is correct, and then I will back propagate that through the network. Does that make sense, everyone? Right. So, this is the context with choice 1, this is the context with choice 2, right. I use all this information to predict a distribution over the different choices that I have, and whichever is the correct choice, I will back propagate that. I will try to maximize that probability, okay. So, what we have seen is like a variety of NLP tasks, all of which have been the network has been adapted to these tasks after it has been pre-trained, right, and we have found the appropriate input representation. In some cases, we had to add the dollar and the appropriate thing to do at the output, which means we ignore the next token prediction and add just one layer which predicts the classes required for this task. Does that make sense? Right. So, that is what we have done in fine tuning. We can see other tasks. Yeah. Now, we look at text generation. So far, what we were doing was basically predicting one class. Now, suppose I want to generate a text. I will give you a premise and complete the story. So, I said once upon a time there was a king, and then it has to generate the remaining 500 tokens to complete this story, right. So, then I have given it some input. So, this is the input that I have given, right, and now I am interested in what it predicts till it gets to the end of the sequence, or it produces this special end of sequence token. Is that okay? Right. So, that is the generation task now, it is not a classification task. So, I have given this 2 inputs, it will pass this through the network and then start computing what comes at every token. It will predict one token, feed that back, predict this token, feed that back, and keep doing this till it reaches a certain length, or it gets this spatial sequence that this is the end of the sequence. I do not want to generate anything after that, okay. on output token. Output would be, so yeah, so suppose at this point it generates a distribution over the entire vocabulary, and 2 was the word with the maximum probability. So then it predicts 2 there. So I like 2 is what your sequence has become. Now this 2 itself would be fed back here. So now your input is I like 2, and it again try to predict a distribution here, and maybe some other word will get a maximum probability there. So let's see. So I like to think that, right? So this is what it has predicted, and after it generates 5 tokens, including the 2 tokens that I had get it, I truncate. So this is what my output would look like, right? So this is adapting this model for text generation kind of tasks. Now, will it produce the same output sequence for a given prompt? Every time I give it I like, will it generate to think that only? If it has generated that once, will it always generate that? Because it is deterministic, right? So I like all, so once you give I like, whatever computations happen here are all deterministic. The same multiplications will happen, the weights are frozen, so some multiplications will happen, you will get some vector here, and when it multiplies it with your output linear matrix, it will give some distribution in which 2 was maximized. No matter how many times I repeat this computation, always 2 will have the maximum probability, right? So whenever I give it I like as the input, it will always generate the third word as 2. Now when I give it I like 2 as the input, it will always generate the fourth word as think. Or not think, like the same word will always get generated at the 4th position, right? So now you will never have variety. And that looks like a useless thing to do, right? Because I might want to generate creative things, right? So once upon a time there was a king. After that you don't want to generate the same story every time, right? You might want to generate different stories. So you don't want this deterministic output. But if you select the maximum token, maximum probability token from here, then you will always get the same sequence generated, right? Because it passed through the network, all the computations are deterministic, and it got 2 as the maximum probability. And if you fed it here, again I like 2 is the sequence that you have given. All the computations that happen after that are going to be deterministic, and maybe think is the maximum probability that gets generated here, and this process repeats, right? So once you give it a prompt, once upon a time there was a king, the entire remaining 5 and 2 tokens will always be the same as long as you give this as the input. And this is not what you want, right? You would want to have different generations every time. So that is something that we will have to understand how to do. So what is our wish list for text generation? That it should not have degenerative, repetitive or incoherent text, right? It should not do like I like to think that, I like to think like, I like to think. It should not generate text like this. It should not generate something which is incoherent. I like to think that reference know how to think best selling book. This is not making any sense, right? So I don't want it to generate such things. I want it to be creative. So I give it the prompt I like, it should generate to read a book. Maybe some other time it should generate to buy a hot beverage. Maybe at some other point it should generate a person who cares about others, right? So it should be able to generate different kinds of sequences, not be repetitive, not be degenerative, not do something incoherent, right? So this is the wish list that we have from what the model should generate. How will we ensure this is something that we learn about in decoding strategies, okay? So now let me just summarize what we have done today, right? So we started off with this idea of language modeling. Then we say that language modeling can be done with transformers. We had 3 different choices there: encoder only, decoder only, encoder decoder only. We first picked up the decoder only choice and studied the GPT architecture. We understood what it is. As I said, once you know the basic transformer architecture, there is much to teach there. You just have to say this exists, this does not exist, remove this block, add this block, and so on, right? And that was the pre-training part which we did with very long continuous sequences of 5 and 2 sentences. And we understood that the entire sequence passes through it, we have masking, and we maximize the probability of every token and backpropagate to the network, right? And we do this massive pre-training. Once the network is pre-trained, we do fine tuning, we allow it to adapt to specific tasks. Initially, we focused on the standard NLU tasks, which is predict the sentiment, given a question, pick up the right choice, given 2 sentences, say whether they are related, not related. But then towards the end of the lecture, which is the slide that I'm on, we went into generation. And that's the wow factor of these current LLMs, right? They're able to generate very coherent text. So we saw how we can use them to generate text. We just give them some input, right? And I chose to give a very simple input, I like, and I want it to complete the sentence. But in the way we are doing it right now, it looks like we'll always get the same input for the same prompt. I will not get a different story every time I start with once upon a time there was a king, right? So I want it to generate different things. For that, we'll have to see how to have decoding strategies which will ensure that for the same prompt, I have some variety in the sequences that I generate. Right? So that's what we'll cover in decoding strategies. So I'll end this lecture here and we'll meet again next week. Okay, thank you.